Now we want to see that if we can simplify this Chebnet, because we had multiple thetas that we wanted to use, and it was a lot of parameters. So we want to reduce that. We want to approximate our essentially filters using a first order approximation. So in that scenario, let's define our convolution as multiplication of this convolution matrix with signal f defined on the graph, just for one dimension. We can write that as we can write this pk of L tilde. We can expand this, write this, and then this whole term is multiplied by f. Okay, so we said that we want to only have a first order approximation. So our k is going to be equal to 1. So I have two terms here that I'm summing. I have T0f plus T1 L tilde f, right? So now I plug in what my L tilde was, which was scaling my normalized Laplacian matrix. So I plug that in, and this is the relation that I have. Now we said that the normalized Laplacian matrix has interval between 0 and 2, so I can approximate that my lambda max is going to be equal to 2 at most. So I plug this 2 into this relation, and I get L minus I over here, right? So this is the relation that we're left with. Now, in the next step, what we want to do is to expand that L, right? We expand that L, and we write it as this relation. It is a normalized Laplacian matrix. A normalized Laplacian matrix is going to be equal to, we're multiplying by d to the minus 1/2 on both sides. And then I'm just writing L down, where Laplacian is equal to the degree matrix minus the adjacency matrix, right? So I plug that in, and this is the relation that I'm left with. So in the next step, what I can do is to separate these. So I have d minus 1/2 to the times d times d minus 1/2 minus d to the minus 1/2 times a times multiplied by d to the minus 1/2 minus I, right? So I expand it that way, and then I realize that this term is equal to just I, and then this other term is equal to, it's a normalized adjacency matrix, right? So now I have, and this V here is just showing that the dimensionality of my identity matrix, right? So I have I here, I have I here. This minus, basically they're going to cancel each other out. And what we're left with is this relation. So now what we want to do is to do parameter sharing. Parameter sharing means that we have some parameter that we learned for some part of our problem, and we have multiple parameters in different parts of the problem. And what we want to do is to use a single parameter instead of learning multiple parameters. So for instance, in the case of basically the sub-tree structures that we learned, we said that we want to take the weight that is aggregating information from different neighborhoods and updating them and apply that for all the nodes in the graph. So, or in the case of multi-relational graphs that we said, we wanted to share between different types of the relations that we have, right? So here what we want to do is to share some parameter theta between these two terms. So that means that I'm going to have theta as my main parameter, which is equal to theta 0 and is equal to minus theta 1, right? So if I write it that way, I can factor this theta out, and I'm gonna left with basically, there should be an F here outside of this, right? So I'm gonna be left with I minus this term times F as here. And it's actually not minus because I said that I'm factoring minus theta 1 out. So it's gonna be I plus d minus 1/2, A d minus 1/2, right? So does it remind anyone of anything? Not yet. All right. So I'm gonna say that let me have some neural network, and I want to use this type of convolution. And I can use this kind of type of convolution by stacking many of these layers, adding a nonlinearity and stacking many of these on top of each other, right? So now what happens is that if I apply multiple of this, because its eigenvalue of this term is outside of essentially 0, 1, it's gonna be unstable. And the problem with that is we don't want unstable. And this problem is because we are stacking too many of these. So in order to avoid that, we're using something called the renormalization trick. And by doing so, we're essentially redefining this relation as we're adding this I directly to the to basically the diagonals of each of these matrices. Oh, basically to the A, and I'm computing D based off of that. So I'm rewriting that as the convolution is equal to theta times D to the minus 1/2, A D to the minus 1/2 F. And these are A tilde, which is just I is basically added to our A. And then the diagonal term is now computed based off of this A, because we want to normalize this new term now. We want to normalize A plus I now, right? So now, writing it this way, we see that this is essentially the graph convolution network that we have, right? That we have basically implemented in our homework system. So I write it in the matrix form, and for the matrix form, instead of having a one-dimensional signal, what I'm going to have is a d-dimensional signal, right? So I have a matrix H, which has on one dimension V, on the to the basically number of different nodes that we have. On the other dimension, we have just the dimension of the embedding D, and then it depends on what level it is on the particular D. So I'm going to have a theta, a learnable parameter that has input dimension D and output dimension D prime, where D is just the size of the embedding at iteration T. D prime is the size of the embedding at iteration T prime. And then for the next layer, I will have the basically embeddings that are of dimension D times D prime, right? So input dimensions D, and for embedding, output dimension D prime. Now I add nonlinearity to this. I'm going to have a GCN layer. So the conclusion that we make is that a basically GCN layer is a first order approximation of ChebNet. So it's a first order approximation of the polynomial, Chebyshev polynomial filters that we defined. So in general, the idea that basically we follow is that if we use something as I plus A, and we construct some polynomial based off of that, this will have two notions. This will have A, gathering information from neighborhood, and it will have I, combining the message of the node itself to the information from the neighborhood. So we see from basically a signal processing perspective how we ended up with the idea of basically message aggregation and combination. And for instance, if we just write I plus A, we will get back our basic GNN model, which was learning two types of weights. It was learning, it has basically some weight, theta n, which was essentially gathering information. So this should be H, not F. So this is basically gathering information from the neighborhood. And then we had another weight, which is representing the importance of the, basically it's just learning a weight corresponding to the information of the node itself. So I'm showing that with theta n, meaning that the theta for the neighborhood aggregation, and then theta v, basically the weight for the node v itself. All right, so just to summarize what we have covered today, we started by reviewing how we have essentially Fourier transform in the Euclidean space. It takes information and it, for example, something that is defined on a grid, it takes that and gives you something which is defined in the frequency domain. And we saw that we have inverse Fourier transform that does the opposite of that, right? So the idea now is that we take the basis, the Fourier basis, and we see that those are essentially eigenvectors of the Laplacian operator defined on the Euclidean domain. And we realized that this Laplacian operator is equal to the Laplace matrix Laplacian matrix of the graphs. So the idea is that we use the same Laplacian matrix, we do an eigendecomposition on this, and we take those eigenvectors and we use that as the basis for our basically graph Fourier transform. So using that, we can take information defined on the nodes of the graph and represented in the spectral domain, which is corresponding to the frequency domain of the basically the classical Fourier transform. Now, using that, we can say that we can define convolution operation in the spectral domain. And then instead of taking our signal, spatially defined signal, and projecting it back to the spectral domain, we are directly defining our basically filters on the spectral domain. So by defining so, and by parameterizing them, we can learn some filters in the spectral domain. Now, if there are two approaches that we can take, we can have spectrum-based models or spectrum-free models, right? So in the spectrum-based models, we are learning a theta and we are using eigenvectors of the graph in order to project them back to the spatial domain, right? But in the, so for instance, we have spectral convolutional neural network, which is one of the first graph neural networks proposed. For spectrum free, and there are two problems with that: the expense that this has, and the fact that it's going to work for the transductive settings only. So what we want to do is to get rid of that U. We want to use a spectrum-free approach. So in the spectrum-free approach, we are not using U, but we're defining it such that we don't need U. For instance, we define it with parameterize our spectral filters with some polynomial of the Laplacian matrix. And then we're just learning the coefficients of that polynomial as our basically training parameters, as our weights of the layers of the network. Right, so we define the convolution as a basically multiplication with some convolution matrix, which we are gonna learn. So, and our basically couple examples we looked was ChebNet, which is using a Chebyshev polynomial in order to approximate the spectral filters. And the last method that we looked was the GCN layer, which was, and how it was essentially defined as a first order approximation of the ChebNet. That's it for today.